Hey everyone, welcome back to Everything is Relative with me, Mr. K. Today we're going to be doing some topical past paper questions on the topic of electromagnetic induction for A-level physics, Cambridge A-level physics, and these questions come from the Papa Cambridge website. So I'll place a link to the website below where you can download the question paper, and my suggestion would be to work with these problems thoroughly and complete all of them before you watch this video so that you could use this video more as a guide to understand where you went wrong when doing your corrections. These past exam questions are invaluable because they do help you prepare for what types of problems you are to expect in the exam. And you do know that magnetic fields is one topic and electromagnetic induction is included in that chapter, but the questions have been separated in the Papa Cambridge website. So today we're going to be doing basically the chapter of magnetic fields, but the topic of electromagnetic induction, which includes things like Faraday's law and Lenz's law. So the first question that we're going to look at, the numbers may not be clear here, so I'll just write it down, but as it's labeled in the Papa Cambridge questions is question 293, and this is the subject code 9702. This is the March exam from 2021, question paper for variant 2, and in that paper this is question number 9. And so if you don't download this paper, you can go and find this very specific exam and look at this question if you want to work on this specific question alone. And the first thing they ask us is to define magnetic flux linkage. Now the definition should be, well, bread and butter for you. These are things that you can memorize. Now, what is magnetic flux linkage? Now, if I think of magnetic flux linkage, it's BAN. So I can always write an equation. If I remember the equation, that will sort of help me with the definition. So phi, which is flux linkage, or magnetic flux rather, multiplied by N gives me the flux linkage. And this is BAN. So for a certain surface, it is the uniform field, or uniform flux density B, times the cross-sectional area A of that surface times the number of turns in the wire. And so this actually helps me write a definition. If I've forgotten what to write, I can use the equation to help me write the definition. So it is simply basically the word version of what I've written there. It is and again, this is something that you will read many times and eventually not forget. It is the product of magnetic flux density. I'm too lazy to write down the word magnetic, but it's the product of flux density, cross-sectional area, or simply area, and the number, I'm going to write numbers NO, but you will have to write the full word, the number of turns, and I'm going to say specifically for a coil whose area is perpendicular. Again, we've ignored the sine theta there because we assume that the area is perpendicular to the field or to the field lines. So it's the product of the flux density area and the number of turns for a coil whose area is perpendicular to the field. And that is your definition of magnetic flux linkage. And so the equation there was helpful in finding or writing that definition. Now the next part of the question says a solenoid of diameter 6 centimeters and 540 turns is placed in a uniform magnetic field as shown in the figure. So we see the field is uniform, it's coming in at right angles to the axis of the solenoid, or actually parallel to the axis of the solenoid, and the diameter of this coil, of this loop, is 6 centimeters and the number of turns is 540. It's obviously been exaggerated in size here. Now the variation with time of the magnetic flux density is shown in the figure. So this field is keeping a constant direction but changing in magnitude, changing in size. So it's getting stronger and weaker. And we are asked to calculate the maximum magnitude of the induced EMF in the solenoid. So there's an EMF induced in the solenoid because there's a magnetic field that's moving into the area of the solenoid and then changing in magnitude. Since it's changing, it will induce an EMF. It will cause current to flow in this coil. How do we find the maximum EMF induced in the coil? Well, what we know is that the EMF induced, I'm going to use the symbol epsilon, but we can use the symbol uppercase E, is proportional to the rate at which the magnetic field is changing. Delta B by delta T. And we'll see where this comes from. So if I look at a graph of B against T, flux density being B and time being T, the rate of change of this graph is delta B, delta T. So if I want the maximum magnitude, so I'm not really cared about the sign here, increasing or decreasing, if I want the maximum magnitude of the EMF, I need to look at where the graph is changing the quickest, where the change is the most rapid. And what I can see is the change is most rapid for the descent, for between time 6 seconds and I think it's 7.2 seconds, as we can read off from the graph. Also be very careful, this flux density is in milliteslas. You should never have a magnetic flux density that's 200 odd teslas. That's way too powerful. So 200 milliteslas and 0, that's the range of values of the magnetic flux density. So what this means is the maximum EMF is at the steepest gradient. And so this you can remember as anytime you see a graph of flux density against time, if you want the maximum EMF, look for where the gradient is the steepest. Again, it asks us for the magnitude, so it doesn't really care about whether the gradient is increasing or decreasing. So this EMF, if I remember my equation, is delta phi by delta t. But I can also write phi as BAN, as I did in the definition. So that's where the definition came in handy. So I'm going to write this as the area of the loop is staying constant and the number of turns is staying constant, but the magnetic flux density is changing with time. So yes, it's delta BAN delta T, but A and N are constants, so I can bring them out. Now what's the area? For the circular loop, it's pi r squared. So it's pi, and we are told the diameter of this loop is 6 centimeters, so it's pi times the radius. Now the radius is half diameter, 0.03 in meters squared. That's the cross-sectional area of the loop, multiplied by the number of turns, which is constant as well, 540, multiplied by the change, or the rate of change of flux density. So I'm now looking at the steepest part of the graph, so I'm ignoring the minus sign. And the flux density goes from 250 milliteslas to 0 milliteslas in a time of, well, 7.2 minus 6 seconds, which is 1.2 seconds. And so this change in flux density is 250 minus 0. And again, this is milliteslas, so we have to multiply that by 10 to the minus 3. It may not be clear, that's a 3, since we have milli. And we divide that by the time it takes for the magnetic flux density to change, which is 7.2 minus 6, or 1.2 seconds. Doing the calculation, what I should find to two significant figures is that this EMF is 0.32 volts. And so the EMF is a constant 0.32 volts for the time in which the flux density is decreasing. Why is it a constant value over that 1.2 seconds? Because the gradient of this graph is constant. So we look at the gradient of the flux density versus time, and we can tell what the EMF is going to be. So this is a common trait. If you ever see a flux density versus time graph, you can use the gradient to find the EMF. A nifty little trick, but that just comes from the mathematics of it all. So the next part of the question says a thin copper sheet X is supported on a rigid rod so that it hangs between the poles of a magnet as shown in the figure. So we have a copper sheet and placed between the poles of the magnet. Remember very well from IGCSE or high school that copper is not magnetic. So what happens if I place the copper sheet between the poles of the magnet? Well, absolutely nothing. So copper is magnetic, and sheet X is then displaced to one side, very importantly, and then released so that it oscillates. So now we generate a motion with this sheet X. A motion sensor is then used to record the displacement of X, and then we replace sheet X with sheet Y, and sheet Y has the same overall dimensions as X, but is cut into the shape shown. So we cut little strips out of sheet X and turn it into sheet Y. So sheet X has a overall greater surface area than y. Y has holes in it. And we can use the motion sensor again to record the displacement as we allow these sheets to oscillate back and forward, as we can see in the arrows. So the sheet moves back and forth. What we find is that a graph of displacement versus time for both x and y is given. And we don't know which one is which. So we have a solid line, which is not really changing with time, which is a nice, very simple harmonic-ish motion. And the dashed line is like simple harmonic motion, but it seems to be damped in some way. So it's not completely simple harmonic. So lo and behold, what does the first question say? State the name of the phenomenon illustrated by the gradual reduction in the amplitude of the dashed line. Now, you have to go back to the topic of oscillations, but you remember that if the amplitude decreases very slightly and takes many oscillations before the system comes to rest, we call this very specific term, we call this light damping. So that's an example of light damping. But as you can imagine, the next question asks us why this light damping happens. So we want to figure out which copper sheet is represented by the dashed line. Deduce which copper sheet is represented by the dashed line and explain your answer using the principles of electromagnetic induction. So very specifically, we are asked to use electromagnetic induction to explain why there's light damping occurring. And we want to explain which copper sheet is undergoing the light damping. Now, what we know about both sheets is that when the sheet oscillates between the poles of the magnet, the sheet cuts lines of magnetic flux. So I'm going to draw these field lines, but we can't see them obviously, but these field lines point from north to south. So we don't really have a north pole, but let's assume that's north and let's assume that's south. It doesn't have to be, again, this is just for demonstration. And the field lines are pointing from north to south. And if the sheet doesn't move, then there's no motion of the sheet relative to the field line. So it's not cutting any field lines. But once the sheet begins to oscillate, then the sheet begins to cut field lines. So when the sheet cuts lines of magnetic flux, what happens is this induces, by definition, we said that when lines of magnetic flux are cut by a conductor, an EMF is induced in the conductor. So copper, although not magnetic, is a conductor. Okay, and an EMF is induced in it, and hence an eddy current. So eddy current may have been removed from the syllabus, but again, electromagnetic induction has not. So an eddy current is produced in the conducting sheet, and these currents cause a resistive force. And these currents cause heating. So the more current I generate, the greater the resistive force, the greater the heating effect, which is going to take energy from the oscillations of the sheet. So I should just write this down, which removes energy from the oscillations. So the energy has to come from somewhere. So a larger current, larger heating means more of a resistive force, which must take away energy from somewhere. It must come from the oscillations. Now what we know is that Y has holes in it. So Y has smaller currents than X, because Y has a smaller surface area, X is a larger surface area. And so what this means is that X is represented by the dashed line. And that's because X shows the much greater damping. And if it's showing greater damping, that means it's undergoing much more of an eddy current, experiencing much more eddy currents. And that's because it has a larger surface area and more currents can flow. So more of the sheet cuts the field lines, inducing an EMF and hence a current. The currents will cause a resistive force, or the currents will remove energy from the oscillations. Since Y has smaller currents than X, X is represented by the dashed line. So this is our answer for what the dashed line represents. The dashed line is representing X, and we also explained using electromagnetic induction why this is the case. These kinds of questions are common, so you be very careful about answering them. it is not correct in any way whatsoever to say that the magnetic field of the copper sheet interacts with the magnetic field of the magnets. Copper itself is not magnetic. You can't say that the north or south pole of the magnets are going to push or pull the copper sheet to or fro. The copper sheet being an conductor is going to have eddy currents induced in it when moved relative to a magnetic field. So just remember that generally these metals that we give you are going to be non-magnetic, but we expect you to apply the electromagnetic induction or Lenz's law to explain what's happening. The next question we'll move on to is numbered question 294, and this is subject code 9702, which is A-level physics, summer of 21, which is May-June 21, and this is question paper 4.1, question number 10. So you can see it regularly comes later on in paper 4. And it says state Lenz's law. And again, this is something you're probably going to be able to do in your sleep. So Lenz's law states that the direction of an induced EMF, so when we induce an EMF by moving a conductor to a relative to a magnetic field or having a changing magnetic field to a stationary conductor, we induce an EMF, but it is such as to oppose the change causing it. So Lenz's law is basically another way of stating the conservation of energy, but the direction of an induced EMF is such as to oppose the change causing it. And so if an induced EMF is generated by a current which generates magnetic fields, then the induced EMF will be in the opposite direction of the initial or original current to ensure that energy is conserved rather than stacking and getting greater with more inductions. And so obviously the next part of the question is going to require some application of Lenz's law. Now we are told that a metal ring is suspended from a fixed point P by means of a thread. The ring is displaced a distance d and then released, and you can see it oscillates between, well, before it even gets to the magnet, the ring oscillates and we count many oscillations. We then add the ring between the poles of a magnet. So we are told that the poles of a magnet are now placed near to the ring so that the ring hangs midway between the poles of the magnet, as we can see in the figure. We then do the same displacement, distance d, and then release the ring, and now the ring completes fewer oscillations before coming to rest. So a common answer for this question is that, well, the ring is metal, so it's magnetic, which immediately we know is not true. But since the ring is magnetic, it gets pulled to either one of the faces and removes energy from the oscillations. And this is not true. We are not told that the ring is magnetic. We are told that the ring is metal, so it is a conductor. So we have to think of the law of electromagnetic induction and Lenz's law in order to answer a question such as this. And the best way to start with a question like this is, like I did with the previous question, the ring cuts lines of magnetic flux. So you're going to see that's my go-to beginning. So the ring cuts lines. Let me just move this down. So again, the flux, the field lines are pointing from north to south. This time we are given the direction of the field, since we are told which is the north pole and which is the south pole of the magnet. And so when stationary, nothing's happening. The ring is not cutting anything. But when moving, the ring is moving, parts of the ring are moving perpendicular to the field lines. And so there's cutting of field lines that are happening. So the ring cuts lines of magnetic flux. And you know what this does, which then induces an EMF in the ring. What does an EMF generate? Well, an EMF generates eddy currents. And eddy currents are hence induced or produced or created in the ring. And these eddy currents give rise, in turn, to its own magnetic field. So the ring will now have its own magnetic field around it. So this gives rise to magnetic fields. But remember, they asked us to state Lenz's law for a very important reason. These magnetic fields that are now induced in the ring, because of the currents induced in the ring, will oppose the magnetic field of the magnet. So whatever the magnet is doing, the ring will do the opposite to conserve Lenz's law. So Lenz's law still holds. And so what we get is a resistive force again, which is created, and this resistive force will again remove energy from the oscillation, or we can say damps the oscillations, which means the same thing. Energy is removed from the oscillations. So again, quite a long answer. And again, it looks shorter because, well, I've written it in a different size. Just maybe write it slightly bigger. So the ring cuts lines of magnetic flux. This induces EMF in the ring. This is by the law of electromagnetic induction. Eddy currents are then produced, which give rise to its own magnetic field. And so now the copper, or the metal ring rather, has a magnetic field around it. It didn't originally have one. It required the induced current to give rise to a magnetic field. And Lenz's law says that the magnetic fields that are created will oppose those of the magnet, and hence resistive forces will cause the oscillation of the ring to be damped, or will remove energy from the oscillation of the magnet. So this is how you again answer a question like this. And there are many like this, and even in this video we'll see quite a few of these. But it's important that you understand that this metal is not necessarily magnetic. And so we have to assume that it's not magnetic, and so the loss of energy comes from the induced currents and hence the induced magnetic field. Now the same question with a bit of a twist in it says the ring in B is now cut so that the shape is shown in the figure. So we now have a piece of the metal ring missing. It doesn't go all the way around. And they asked us to explain why, when the procedure in B is repeated, so the ring oscillates between the poles of the magnet, the cut ring completes more oscillations than the complete ring when oscillating between the poles of the magnet. So basically this ring that we have in front of us is less damped. It undergoes less damping than the previous ring. And the only difference is that we cut a piece of the ring out. So how could this possibly happen? Now, we still have eddy currents produced in this ring, but what can we see about the eddy currents? Well, the eddy currents cannot pass all the way around the ring because the ring is cut. And so we have fewer or less of an eddy current, or less eddy currents around the ring. And so they are smaller. So the eddy currents are in totality are smaller, which means that the magnetic field created around the ring is smaller, which means that the resistive force, the thing that's going to generate the damping, is now smaller. And since the resistive force is smaller, there's less damping. And so the more I cut out of the ring, the less resistance I'd have, because there are less eddy currents, fewer eddy currents meaning smaller magnetic fields, meaning less opposition to the original magnetic field and hence less damping. So again, I have to make use of the knowledge of this metal being a conductor, not necessarily being magnetic. So be very wary of this kind of question. And so you see that out of a 9-mark question, there's 3 marks and 4, that's 7 marks out of 9, which comes from a very sort of conceptual kind of question. Explain, discuss, deduce, and these kinds of things. So be very well prepared for questions like these in your exam. Not everything is going to be a calculation. So some of you may enjoy questions like these, some of you may shy away from them, but be prepared for them. They may count a significant portion of your exam. Now the next question is numbered 295, and this is subject code again 9702. This is from summer 2021, and this is question paper 4, variant 2, and this is question number 9. And the first part of the question says, state two situations in which a charged particle in a magnetic field does not experience a force. Might be quite weird. Why would a charged particle in a magnetic field not feel a force? Well, the first thing I want to do is write the force that a charged particle feels when it's in a magnetic field. F is B Q V sine theta. And what I can see from this equation is that there's a force on the charged particle. So I know that the particle is charged, so it definitely has a charge Q. There is a magnetic field, so there's definitely a B. But the two things that don't necessarily have to exist, given the situation, is V and sine theta. So those are the two situations in which a charged particle will not experience a force. So the first one of these would be when V is equal to 0. So simply put, the particle is stationary. Stationary charges do not feel forces in magnetic fields. So I can simply say the particle is stationary. And what will be the second scenario? Well, the second scenario will involve theta. So if sine theta is equal to 1, I have the maximum force. But is there any point where sine theta equals 0? Yes, when theta equals 0. If theta is 0, that means the motion of the particle and the field lines are parallel. So the second scenario happens when the particle moves parallel to the field or to the field lines, to be more precise. And so the particle moves parallel to the field lines. That's the second scenario in which a charged particle moving in a field will, or rather a charged particle in a magnetic field will not feel a force if the particle is moving parallel or anti-parallel to the field lines at an angle of 0 or 180 degrees to the field lines. And so that was a quick examination of the equation of the magnetic force on a particle will help us deduce what two scenarios they were. You didn't need to write the equation down, but it sometimes helps. Next, we are told that a loosely coiled metal spring is suspended from a fixed point, as shown in the figure. And again, it's a metal spring, doesn't say anything about the type of metal, but electrical connections are made to the ends of the spring by means of a flexible lead. The length of the spring is measured before the switch is closed and then again after the switch is closed. So, kind of a weird type of question. Where are they going with this? When the switch is closed, a magnetic field is set up around each coil of the spring. By reference to these magnetic fields, explain why there's a change in length of the spring and state whether the spring extends or contracts. So again, quite a tricky question for 4 marks, very conceptual in nature. So basically, they want to know when I close the switch and when I create a current in the circuit of which the spring is a part, before any oscillations happen, this spring changes length. So it's resting very nicely in equilibrium, but when I close the switch and pass a current through it, weirdly the length of the spring changes. And it has nothing to do with the mass because it's already been extended by the mass. So it must be because of some other reason. And we can see clearly that they say that by reference to magnetic fields. So not the change in length because of the mass, but because of something else. So what do I do? This is quite a tricky situation. So what I'm going to do is try to use this diagram to help understand what's happening. So here I have a positive terminal and then I have a negative terminal. So what this means is if I follow the path of the current's going to flow in that direction here, and the other end of the same coil is going to move in that direction. Then it's going to go to the adjacent coil, the coil directly below it, and it's going to move in the same direction to the coils below. And what I can see is that these directions are the same. So that the same direction as that, and that's the same direction as that. So in adjacent coils, the current is always moving in the same direction. Immediately, if you remember your theory, you know that if current is in the same direction for two current carrying wires, then the force between those wires will be attractive. And so we can see there immediately that there's going to be an attraction which is going to cause the adjacent coils to move toward each other, which will decrease the overall length of the spring. But we need to have more content than that. So how do I, well, maybe I can draw it slightly better. Let's draw a half coil there, and then the adjacent half coil directly below it. And I have the current moving in the same direction. Now the current in the first coil induces a magnetic field, which is going to be circular in shape, at least for a really small area. And the magnetic field is going to loop around that coil and interact with the current in the second coil. And so the field is B, the current is I, and these are two adjacent coils. So what this means is that immediately I can see that the current is perpendicular to the field. So you see the field is looping around and the current is moving at right angles to the field at any point. What this means, what we know from using Fleming's left-hand rule, is that the force that is produced on every coil of wire must be perpendicular to both of these. So the force is perpendicular to the current, which is also perpendicular to the magnetic field. So we have a right-hand system. So the field is pointing, perpendicular to the current at any point, and the force that's being produced will be perpendicular to both of them. And so basically what happens is that a force is produced along the axis of the spring. And so it's going to cause a contraction or expansion, but we already know it's a contraction along the axis of the spring, which means the length of the wire is going to decrease. So the length of the spring is going to decrease. So how do we answer this, or try to answer this in a very sort of clever way? So what we know is that each coil of the wire is normal to the magnetic field, or perpendicular, whichever word suits you. Normal is just easier to write. It's normal to the field produced by the adjacent coil. So the current in each coil produces a field which is felt by the adjacent coil, and the field and current are normal. The current in each coil then experiences a force due to this field, due to the magnetic field, to be more specific. And what we know is that this force is perpendicular to the field and to the current. And Fleming's left-hand rule can tell us this. What this means is that we've already determined, and we know from theory, that the force between coils is attractive, because when current is in the same direction, the force is attractive. When current is in opposite direction, the force is repulsive. And since all the coils are pulling at one another, the spring contracts. And so what you would notice if you are observing this is actually the spring getting smaller in size, actually contracting upwards, even though the mass is not changing. So this is something you could possibly do if you could pass a current through a spring. But each coil of the wire is normal to the field produced by the adjacent coil, and the current in each coil experiences a force due to the magnetic field. The force is perpendicular to the field and to the current, and so must lie along the axis of the spring, and so the force between the coils is attractive and the spring contracts. So it's a very tricky type of question, this one. The little hint that we got was specifically saying that by using the reference to these magnetic fields, and was there any other hint we could say? Loosely coiled wire could have helped, But again, it was a lot of conceptual thinking that we had to put our minds to score these 4 marks. But again, they did say reference to magnetic field, so you could have explained something about induction and about the force that adjacent coils feel due to the current in each wire. So even if you couldn't come to a conclusion, you could lead to some sort of idea about induction. Now the next question says, with the switch in B closed, the small mass on the free end of the spring is now made to oscillate vertically. So now we close the circuit, but we make the mass oscillate. So initially the mass was just stationary, but now the mass oscillates. And we are told to use the principles of electromagnetic induction to explain why small fluctuations in the current in the spring are found to occur. Okay, we don't know what the small fluctuations are, but apparently the current in the spring is going to change very slightly. So how is this going to happen? So basically, as the mass oscillates, the coils get further apart from each other and then closer together. Now, also what we know from simple harmonic motion, or even just from oscillations, is that the rate at which something is moving when oscillating is constantly changing. And even acceleration is constantly changing with simple harmonic motion. So these springs are moving at different rates constantly. They are spreading apart, coming together, spreading apart, and so on. If they are moving at different rates, they are cutting lines of magnetic flux at different rates. So the current through each loop is not changing, but they are producing fields that are remaining constant, but they are moving away from or toward each other. So they're going to cut adjacent flux lines at different rates. If they do this, they're going to induce varying EMFs in the coils. And this is going to cause a very slight fluctuation in the current in those coils. So basically what I'm trying to say is that as the coils oscillate, so as they move up and down, they cut lines of magnetic flux, which we've already explained in the previous question. But they do so, it's very important that we explain that they do so at a varying rate. So they spread out, they get closer, and so they're cutting lines at a differing rate, because the mass will accelerate as it moves down, and then through the equilibrium after the equilibrium position, it will slow down, reach zero, and then the entire process happens. So the rate at which flux lines are being cut changes, which means the induced EMF, so this induces an EMF that's varying as well, uses a varying EMF in the coils themselves. And so if I'm applying a constant current and then I'm noticing a varied EMF being induced in the coils, I'll notice small fluctuations in the current if I had an ammeter across any point in the coils. And so hence I get a changing current in the coils of the spring or in the spring itself. And so this is also a very sort of intuitive question. You have to think of the principles of electromagnetic induction, and you'd have to know what's happening in the oscillation. So the rate of magnetic flux being cut is changing, it's a varying rate, and so the induced EMF is varying, and hence the current is constantly fluctuating. It might be a small fluctuation, but it's still a fluctuation nonetheless. So a very interesting question, and you can see that the questions vary, well, quite significantly, but the ideas remain the same. The idea to understand induction and Lenz's law are very important. The next question is number 297, and again, this is 9702. This is from the March exam of 2020. It's question paper 4, variant 2, and it's question number 3. Now you can see this is a very oscillation type question. It says a body undergoes simple harmonic motion. The variation with displacement x of its velocity is shown in the figure. We get a nice elliptical graph, and we are asked to state the amplitude x0 of the oscillations. Now we know the amplitude of the oscillations happens when the velocity is equal to 0. If you think of a mass on a spring, when the spring is maximally extended. And so if I look at this graph and look where v is equal to 0, I can read the amplitude either direction. I'm going to get the same value on the positive or negative side. And so if I just want the number, the magnitude of this amplitude, it would be 0.05 meters, the point that I've marked with an X. So that's the maximum displacement of whatever object this is undergoing simple harmonic motion, the maximum distance from its starting position. We're then asked to find the period of these oscillations. That's a bit difficult. What can I take from this? Well, I know that the period, t, is 2 pi over the angular frequency omega. But the angular frequency is the thing that's difficult to understand. What I can determine from this graph is x naught and also v naught. I can determine the maximum speed that the object will take when it's passing through equilibrium. But what I know is, again from theory, v naught is equal to x naught omega. So actually I can write omega as v naught over x naught. So I can write this. I can find the period t by writing this as 2 pi x naught divided by the maximum speed v naught. And both of these values I know. That's 2 pi times the amplitude, which I said was 0.05 in meters, so I can leave that as is. And the maximum speed, thankfully this is given in SI units, meters per second. If I look at my graph, is 0.42 meters per second. And so this is 0.42. And what I get for my period would be 0.748 seconds, which to two significant figures is 0.75. So that's how I would find the period if I only knew the amplitude and the maximum speed of my oscillating object. Now part 3 says on the figure, very specifically on the figure, label with a P a point where the body has maximum potential energy. So again, I'm just going to assume that this is a mass oscillating on a spring, so potential energy would be elastic potential energy. The maximum elastic potential energy will happen when the object has zero velocity, when the spring is maximally extended. And so this would be a point P here, zero speed and maximum extension. Another possible point for P could be here, in the opposite direction. So above or below equilibrium, or to the left or to the right of equilibrium, either way. So that's the point P where there would be maximum potential energy. They only asked us for 1, so I'm only going to mark 1. If you mark 2, you are very likely of making a mistake of contradicting yourself or writing one correct and one incorrect answer, in which case you will not score the mark. So be very wary. Only answer what you expected to answer. Now, the next part of the question says a bar magnet is suspended from the free end of the spring. One pole of the magnet is situated in a coil of wire, and the wire is connected in series with a switch and a resistor. The switch is open, the magnet is displaced vertically and then released, and the magnet oscillates with simple harmonic motion. First things first, state Faraday's law of electromagnetic induction. So, but for a warm-up question. Again, how do I remember it? Well, I remember the equation. The induced EMF is directly proportional to the magnetic flux linkage delta n phi by delta t, the rate of change of magnetic flux linkage. And then I can use this mathematical equation to formulate a definition. So what I can say is that the induced EMF is directly proportional to the rate of change of magnetic flux linkage. So an induced EMF is directly proportional to the rate of change of magnetic flux linkage. And this is a definition of Faraday's law of electromagnetic induction. So an EMF is greater when the flux linkage is changing more rapidly. And an EMF is smaller when the flux linkage is changing more gradually. Now, obviously, there's going to be some application of this in the next question. We're told that the switch is now closed, and we are asked to explain why the oscillation of the magnets are damped, of the magnet rather, is damped. So, moving the magnet in this coil, with the current in the coil, is going to do something. It's going to stop the magnet's motion eventually. It's going to damp this motion. Now, the first thing that happens is that there's a current in the coil. And the current in the coil will produce a magnetic field around the coil. So we know that the current in the coil will induce its own magnetic field. And this magnetic field will obviously exist around the coils of the wire. So I can simply say the current in the coil produces a magnetic field around it. Now the current induced in the coil, not the current that's generated by the power source, by the battery, but the current that's induced in the coil, due to the changing magnetic field as the magnet moves relative to the coil. I can simply say the current induced to the coil due to the changing magnetic field or due to the magnet will, thanks to Lenz's law, oppose the motion of the magnet. And what does it do? If it's going to oppose the motion of the magnet, it's going to remove energy from its oscillations. And so the oscillations will be damped. So the current that is induced in this coil, so as the magnet moves relative to the coil, the magnet induces a current in the coil. The current that's induced in the coil is going to oppose the current that already exists in the coil, going to oppose the motion of the magnet. And if it opposes the motion of the magnet, it's going to damp the oscillations. So energy will be taken away from the oscillations of the magnet, and the energy will then come from the oscillating magnet. And so those resistive forces will damp the oscillations. Energy will be removed from the system in that way. And so again, another application of the electromagnetic induction, and that's why we needed to explain or state Faraday's law before answering this question. So also be very careful about when you see magnets moving relative to coils, immediately think of electromagnetic induction. And then if you want to talk about things like damping or energy being removed, you're also going to think of Lenz's law about the opposition of magnetic fields and the opposition of currents and so on. Now, the last question that I'm going to do for this video is the next question, 298, as numbered in the Papa Cambridge worksheet. That's 9702. This is from summer 20, June 2020. This is from question paper 4, variant 1. And this is question number 9. Now we are told that a coil of wire is situated in a uniform magnetic field of flux density B. The coil has a diameter of 3.6 centimeters and consists of 350 turns of wire. So quite straightforward. Uniform field, coil with 350 turns. What happens? Well, in this way, basically nothing. But, we are told something special. The variation with time of B is shown. So B is not remaining constant. B is changing with time. Now something is going to happen in this coil. We are asked to show that for time 0 to 0.2 seconds, the EMF induced in the coil is 0.08 volts. So we've done this before. So now we're looking at the part in which the magnetic flux density is increasing. So we ramp up the field, keeping the direction always perpendicular to the area. Number of turns remain constant. We want to find the EMF induced only for the first 0.2 seconds. I know that the EMF induced will be constant because the gradient of this line is constant. And the EMF induced E is, by definition, delta n phi by delta t, the rate of change of magnetic flux linkage, which I can write as delta ban, delta BAN by delta t. Now the field lines are perpendicular to the area of the coil, so I don't have to worry about sign of anything. The area is constant and the number of turns is constant. So I can write this as AN and the rate of change of flux linkage. Now the area is circular, pi r squared, pi times the radius. I'm not given the radius, but I am given the diameter. Guess what? If I divide the diameter by 2, I get the radius. Don't tell anyone. So this is pi times the radius 0.018 meters squared times the number of turns, which they give me as 350, multiplied by the final flux linkage, which is 45, if we do this accurately, into 45 minus the initial flux linkage is 0. And again, this is milliteslas. Be very careful of the units in your graph. So that's times 10 to the minus 3. And I divide this by the change in time, which is 0.2 seconds. 0.2 minus 0 seconds, which is 0.2 seconds. And what I should find, if my calculator is working, 0.08 volts. And it's written in this way because there needs to be two significant figures. Because my least number of significant figures in this calculation is 2. And so it does check out, and I do get the value that was required. Now the next part of the question says, on the axis of the figure given, can you show the variation of the with time of the induced EMF, E, for the time t is equal to 0 to t is equal to 0.8 seconds. So basically the variation with the EMF for the entire duration of the change in magnetic flux. So we have a bit more work that we need to do here. So I need to draw a graph of the EMF against time. So how do I do this? Well, the good thing for me is that I know that the EMF for the first 0.2 seconds is constant. I've calculated it and I've shown that it's 0.08 volts. And I can then draw this. So the first 0.2 seconds, 0.8 seconds would be here and here, and it's not changing with time. So I would take my pencil, and in your case a ruler, and I would draw a straight horizontal line. Probably better if I just draw a horizontal line in that way. Obviously not making it too thick, I'm just making it thick so that you can actually see the 2 points. So it's a straight horizontal line for the first 0.2 seconds. Gradient is constant, and so the EMF remains constant. For the next 0.2 seconds, from 0.2 to 0.4, I have a flat horizontal line for the flux density. If EMF is rate of change of magnetic flux density, but the flux density is not changing, there is no EMF induced for the next 0.2 seconds. So what that means is for the next 0.2 seconds, again, I'm only asked to sketch a graph, but I'm going to have 0 EMF being produced for that time. And so I have another horizontal line that is again straight. And now the horizontal line is just 0. So you can see this graph is just a compilation of horizontal lines. And lastly, I need to do the last 0.4 seconds. In the last 0.4 seconds, the gradient is not as steep, but it's decreasing from 45 to 0 millitesla. So the flux density is decreasing from 45 to 0 milliteslas. So I actually need to calculate it because there's no way I can just simply identify what it needs to be. Thankfully, the calculation is not as difficult because it actually hinges on the calculation that I've done previously. So from t is equal to 0.4 seconds to t equal to 0.8 seconds, what I can do is I can say, well, E is equal to, wait a minute, to the same calculation I did before, pi times 0.018 squared times 350 and multiplied by, wait, the change in the magnetic field is the same. Maybe in the opposite direction, but it's the same. 0 minus 45, which I've done before. The only difference is that the time is now doubled. It's 0.4 seconds. So I'm dividing by twice as much as I was before. So what I'll get is a negative value with half the magnitude of the EMF for the first 0.2 seconds. So I'll get 0.04 volts. But now the minus sign is very important because initially the gradient was increasing, now the gradient is decreasing. If the gradient is decreasing, then I have a negative EMF produced, current moving in the opposite direction, it's flipping direction. And so what I have from 0.4 seconds to 0.8 seconds is, I have to count this to make sure it is 0.4 volts all the way. So another horizontal line rather, but at a constant or negative rather, 0.04 volts. So I'll write down these important values. 0.08 volts, obviously 0, and minus 0.04 volts. And so we can see that our EMF consists of horizontal lines, because they are constant when the gradient of the flux density versus time graph is constant, and they change direction when the graph of B against T changes direction. So increasing means a positive induced EMF, decreasing means a negative induced EMF. Or we can do the other way around. Again, the sign is just by convention here. So we could have the axes flipped. We could have the first line below the x-axis and the second part of the line above, provided there's a difference between the signs of the values. And so this is how we plot a graph of EMF against time if we are given a graph of flux density against time. So a good skill to learn, how to be able to sketch these graphs if you are given other values, or given another graph, as we are in this case. And the last part of this question says a bar magnet is held a small distance above the surface of an aluminium disc by means of a rod, as shown in the figure. The aluminium disc is supported horizontally and held stationary, and the magnet is rotated about a vertical axis at a constant speed. Use the laws of electromagnetic induction to explain why there is a torque acting on the aluminium disc. So basically what they're asking us is they're saying, hey, here's a magnet and here's an aluminium disc. Aluminium, again, is not magnetic. It's not going to be attracted towards or repelled from this magnet. But it will start spinning because they say there's going to be a torque acting on the aluminium disc when the magnet starts spinning. And so I need to explain why. So again, I'm going to go to my ideas about electromagnetic induction. So first thing I say, like I always like to say, is that lines of magnetic flux are cut by the disk, or cut the disk. When this happens, this induces an EMF in the disk. So it is not magnetic, but it is a conductor. So an EMF will be induced in the disk, which causes eddy currents. So the EMF in turn induces eddy currents in the disk. The eddy currents in the disk then generate its own magnetic field, and the magnetic field of the disk interacts with the magnetic field, or the magnetic field of the magnet, and causes a force on the disk. So you can see that initially this aluminium is not magnetic. But when the aluminium moves relative to the magnet, or when the magnet moves relative to the aluminium, it induces an EMF in the disk. When the EMF is induced, then eddy currents are induced, which causes the disk itself to interact with the magnetic field of the magnet and causes a force on the disk. So basically the disk is going to move, and it'll move in the opposite direction to the magnet due to Lenz's law. And so you can see that the aluminium disk is initially stationary, but will start to rotate when the magnet begins to rotate because of the eddy currents and hence the opposing force that's created on it. So again, this is an application of the law of electromagnetic induction. And you can see there are very interesting examples that will require your application of the knowledge. There's rings moving between the poles of magnets. There's a magnet rotating relative to a fixed aluminium disk, but the ideas remain the same. Do you know what happens when a magnet moves relative to a conductor, or vice versa? And then can you use that knowledge to then explain what the question is asking? Why is there torque? Why is there a damping or a force, etc.? But basically the underlying principles are all the same. So understand the principles and everything else eventually becomes better with time. So the next time I see you, maybe we'll do a video with some topical problems on quantum physics or nuclear physics. We'll try to get through as many as we can. Then at some point, paper 5 as well, which I know is quite tricky and your exams are looming. So we'll try to get that done very soon. But for now, that's all from me, Mr. K. Please leave a like, subscribe, comment on this video if you think it helped, and give me any suggestions that you'd like to see in future upcoming videos. But that's all from me for now, Mr. K. I'll see you next time when everything is relative.